Good afternoon all. So we'll start for today's session. And last time that was our first physics 2025 class. We were discussing about like introduction to the physics and subject, introduction to the subject, as well as some of the theories behind units, dimensional quantities of physical objects, and what are the basic units we are using, and what is the definition of them and their derivations and applications. And we went up to derived units. Derived units in the sense they are not among those 7 basic units, but they are from basic units that we are deriving from those fundamental units and using for define or provide the definitions or application in our day-to-day physics theories. Right. Then to complete that section, we need to discuss another 3 sections. And today's plan is like this. We'll complete the unit section. The first thing is we'll discuss about derived units with some names. Derived units with specific names. Then prefixes of units. Prefixes of units. Then rules of writing or representing units. Then dimensional analysis. This is today's plan. So we'll rush through first 3 topics. They are not that difficult, much theories, and then dimensional analysis. It contains bit manipulations and calculations we need to follow through. So we'll do much concentration on this, but understanding of these 3 concepts too important when we are working with physics, and when we are working with experiments, and when we are representing data and results of our experiments and mathematical problems. Right. Okay. Derived units with specific names mean there are units. I'm not going to give you all the units what we are having with specific names, but few of them for you to understand. There are things like that. For example, okay, I'll give you some examples. Okay, we'll write a chart like this: physical quantity. Then derived unit name, derived unit name, then derived unit symbol. why I am specifying or specially discussing on these physical quantities with specific names is that because there's a rule, or there are rules when we are representing or when we are providing units which contain a specific name. Most of the time the name is a scientist's name, and later on in that third topic today we are discussing about rules we should follow when we are dealing with specific names or scientist's name when we are writing units. And this is the introduction. Okay, let's say first unit, frequency. Frequency is defined as number of cycles per second or per unit type. Especially it's coming under waves and progressions. And when we are discussing about wave or cyclic patterns, then the frequency term comes. And when we are in that particular unit, then you will get deeper understanding of what is the meaning of frequency. And it's simply 1 over second, but later on we will discuss those things. But here I am giving you an introduction about units of specific names. And the unit name, all simple, we have to write HERTZ, Hertz, one of the scientist's name, and derived unit symbol, that is capital H and simple Z. Even though we are writing even though the rule for writing scientist's name is with first letter capital but not the other letters capital, we have to follow those letters in simple context or the simple form. And next, the more familiar or mostly used term in physics, especially when we are discussing or when we are dealing with mechanics or Newton's laws or Newton's laws in motion, the force, and the derived unit is Newton, and its symbol is capital N. Its symbol is capital N. Then next, pressure, or let's say stress. In some cases, stress also comes when we are discussing about physical quantity, pressure or stress. Both are equal form of physical quantities, but application area might differ. That's why I use both the terms. And the unit name is Pascal, and its symbol is capital P, simple A. Then either energy or heat or work done, right, all are sort of same physical quantity but different applications, but all share same unit, that is called joule, J O U L E, and its symbol is capital J. Then another thing mostly we are using in our mechanics lessons, power. Power is rate of work done or work done per unit time, that is with the unit called watt, W8ET, that to purchase, to give purchase to the much well-known scientist James Watt, who invented about the steam engine and first mechanized engines. So then the symbol is W, capital W, right? Those are few examples for units which comes with specific names and especially with scientists' names. Copy this. Then there are not many more, not only this, but as an introduction, I gave you these things. Later on, when you are getting specific unit names, especially for derived units, then you can recall this lesson, what we learned. Right, copy this, then I will erase, but it's continue. We continue, means there are more to be learned. This is an introduction. Okay, I'll erase this. I hope you copied it. Then I'll erase this. Right. Then another important concept we should aware of, that is prefixes we are using with units. Why prefixes is that, you know, when we want to present, or we want to represent, or we want to produce a bigger number or very smaller number, then either we have to use much more decimal places or much more zeros to represent that tens, hundreds, thousands locations. But in physics, it's not a proper way, or it is not the way we are representing those symbols or those numbers, and we are using prefixes. With prefixes, it's easier to represent smaller numbers or bigger numbers. So we will discuss about those prefixes, and especially when we are dealing with some quantities like for example capacitance. Most of the time capacitors are very tiny, small numbers. What we are using, the devices what we are using in day-to-day applications, so they are not bigger quantities. And then next thing is the resistance. Most of the resistance values are much bigger values. For day-to-day applications, we are using resistance with some kilo range, mega range, like that. Then you will understand what is kilo, what is mega once we discuss about these prefixes. And even the frequencies. Then when we are discussing about electromagnetic spectrum, and there you are getting terahertz, gigahertz, megahertz, kilohertz, then some tiny numbers. Then for those things we are using prefixes to represent the numbers very convenient. So then we will discuss prefixes using unit representation. Prefixes used in prefixes used to represent units. Prefixes used to represent units and physical quantity, units and their values. So I'll divide the board into two. It is easy as to see both in one page and write. So we see what are those prefixes. Right. We'll do a chart like this. Prefix, and its symbol and value. This side also same. Why? Because this table contains bit more data, so that we need to use both the sides. Yeah, sorry about this thing. I'm not very good in drawing straight lines. Anyway, this is pretty much okay. Yeah. Okay. Then we'll go with higher side. Yeah. The 10 to power 18, that called x star, EXTA, that the symbol, I'm sorry, hexa, that this 10 to power 18, simply we are so calling it as hexa, and symbol is x. Then 10 to 15, symbol is p, and it's 10 to power 15, 10 to the power 15. Then tera, that is, the symbol is capital T and the value is 10 to 12. 10 to 12. Then, but maybe this is much familiar, giga. Giga is capital G and it is 10 to the power 9. Then mega, that is capital M and that is 10 to the power 6. Then kilo, then here the symbol is simple k, the symbol is simple k, non dot, and that is 10 to the power 3. Right. Then hectare, that is 10 to the power, the symbol is simple h, that is 10 to the power 2. That is 10 to the power 2. then deca, that is d, that is 10, 10 to the power 1 or 10. Because that especially that hectadeca is, I'm sorry, this is k, and hectadeca is not that much in use in day-to-day applications, but in some of the physics problems, or some of the problems like they're discussing about 1/10 of main quantity or 10th of the main quantity, they might use this deca and hectare terms. And then we'll discuss about the other side, that is deci. That symbol is simple d, and it's 1/10, 10 to the power minus 1. Then centi, the symbol is simple c, that is 10 to the minus 2, 1/100th of the main quantity. That is deciliter. The deciliter term comes most of the times, and centimeter it's coming. So we know centimeter, but we don't know, maybe we are not much aware of the meaning of the centimeter, but it's 1/100th of a meter, that is why it is centimeter. Then next term is milli, M-I-L-I, the symbol is M, that is 1,000th of a main unit, 1,000th of a main unit, that is we know millimeters. We know we are discussing about millimeters, that is 1,000 of a meter is 1 millimeter, that is why the milli we are using. Then next term is micro. The next term is micro. Yeah, the micro we are not using that. We are using this term, and it's 1/10 to the minus 6, 1 millionth, maybe. Remembering 10 to the minus t is easy than 1 millionth. Then nano, this is mu, the symbol is mu, and the next one is nano. The symbol is simple n, that is 10 to the minus 9, 10 to the minus 9. Then pico, P-I-C-O, symbol is simple p, and size is 10 to the minus 12. Symbol is simple p, and size is 10 to the minus 12. But these two units are not that familiar, but better you know that. That is femto. Symbol is simple f, and that is 10 to the minus 15. 10 to the minus 15. Next one is atto, A-T-T-O, and symbol is simple A, and value is 10 to the minus 18. Yeah. You better know these prefixes, mostly this range from maybe tera to deca. In higher range, yeah, we are using, and tens positive range, I mean, and here mostly up to pico we are using in tens negative range, or that's the fractions. When we are dealing with fractions, yes, up to pico most of the time we are using. And nano, yeah, nanotechnology. That nanotechnology means, it relates to the size, later on maybe advanced electronics or advanced physics. You will learn about nanotechnology. If you are interested on learning that, or you can read on that. Right. Hope it's clear. And if you are having any doubt, you may text me, or you may let me know to explain further. But better you keep this as a record, and with applications later on you can recall this and you can get a knowledge about these prefixes what we discussed. Right. By assuming that it is clear to you, I'll move to the next section. That is rules to follow when we are representing or presenting units. This is also important, even though we are not giving much importance to these concepts. Why? Because correct representation of data means both value as well as the units. So when we are dealing with proper units and proper values, we have to represent the unit, because with value without a unit is not having any meaning. Well, for example, 5 we don't know number of people or number of students or rupees or dollars or meters. Yes, we have to represent the value with a unit. And also, but units not always going with its proper value, it's the face value. In some cases we have to use prefixes and some prefixes, as well as in some units they are not fundamental units, they are derived units. So it contains not only one symbol, it contains more than one symbol. In that time we should follow set of rules. We should follow set of rules when representing units. Rules to follow, to be followed when, simply we'll say writing SI units. First thing, I'll dictate. You can make a note on that. The first thing is, we write like this. Some units contain specific names, particularly with scientist names, and in that case, unit name we have to write with small letters, simple letters like this. The Newton, the unit Newton, unit name is Newton. If this is not at a start of a sentence, then we have to write Newton all simple letters, because we are discussing about the unit name, not the person's name. If we want to discuss about person's name, then definitely it should be capital, the proper name. But this time the unit name Newton. For example, Hertz, then Pascal, right? So the unit name should contain all simple letters. Right. Next thing is all units names, if it is not a specific derived name or if it is not a scientist's name, then all units symbols are or unit symbols are simple. In general, all unit symbols are simple letters. If it is not a specific name, such as a scientist name. For example, meter, the symbol is M. Kilogram, symbol is kg. And second, the symbol is simple S. That is the third rule. If unit name is in general, unit names are simple, unit symbols are simple letters if it is not a specific name. Right. The third one, if unit name is a specific one, then unit symbol is always capital but only the first letter. If specific name unit symbol first letter capital. For example, Newton. The unit is Newton and symbol is capital N. Newton. Unit is capital N. And Kelvin, unit is Kelvin. See, I am writing all simple letters, but symbol is capital K. Then unit is Pascal and unit name is capital P, simple A. And unit name is Hertz and its symbol is capital S H, simple Z. See, the first letter only capital, not the rest. Rest are simple letters. Next thing is, when we are writing value and the unit, we always should keep space in between value and the unit. It's like this. The fourth rule, space between the value and the units. For example, let's say 15 kilogram. This is correct. 15 kilogram. This is correct. But if you write 15 kilogram without space, this is not correct. This is not correct. Right? Then let's say 100 meters. 100 meters, you have to write, yes, this is correct. 100, then space meters. Okay, but here I'll discuss the next slide, next condition. When we are having multiple units, what should be followed? Here we are having one single unit for this quantity. So representation is quantity and unit, but with a space in between. Here we can note that we are having one unit type. If you are having any doubt or not understanding, make a message. Then we can discuss further, or I'll explain further on the thing. Right. Next, if it contains multiple units. If it contains multiple units. Multiple units or more than one unit should be separated created by a space in between. What this is saying is, for example, my acceleration is 15 meters per second square. My acceleration is 15 meters per second square. Here, yes, what I have to do is, I have to keep a space here and space here. Oh, otherwise, this will be read as milliseconds if I omit this space. So, the correct definition of this representation is 15 meters per square seconds. Right? Meters per square second or second square. Right, second square, that is the common meters per second square. Square second. Square second. If I write, okay, if I write this way, if I write this way, 15 meter here, I don't have any space between M and S. So this is read as 15 milli second square or milli square second. Now M is used as a prefix. M is used as a prefix now. Because M is not considered as a unit now, it's considered as a prefix. So always, if it is not a prefix, then you have to use, because this is the M used as a unit symbol, then definitely you have to keep a space in between. Keep a space in between. Next thing is when we are writing units, we are not keeping any dots or full stops. No dots or full stop when writing units. Like this, 15 kilometer, this is correct, and this is 15 dot kilometer, this is wrong, or 15 kilometer dot, this is also wrong. This is correct. And this is not correct. And this also not correct. This also not correct. So we are not keeping any dots when we are writing units. That is, we are not keeping any full stops or unit dots when we are writing units. Okay. Next one, when we are writing derived units, either if it's a subtraction or division, it's a division of units, division of in derived units, division can be represented with slash symbol or negative index. Negative index. I'll explain. It's like this. The velocity is defined as distance over time, displacement over time. Okay. So velocity, let's say v, it is displacement is with units meters and time is with seconds. So 5 meters per second velocity we can represent as 5 meters per second or as negative index, that is I can take s to top numerator top, and I can take or change its index to -1. What I can write 5 meters per second. But here keep in mind we have to keep a space in between. So this both of them are correct. Both of them are correct. Correct representation of derived symbols. When division is used. Next, we'll discuss if my derived is with more than one divisions. If my derived is more than one division, it is not correct to use more than one slashes. It's not correct to use more than one slashes. If derived unit is with more divisions, not correct to not correct to use more than one slash symbol. In this case, either we have to use the parenthesis or brackets or minus index. Either brackets or minus index to be used. I'll explain you what that means. For example, joules per mole per Kelvin. Joules per mole per Kelvin or joules per Kelvin per mole. Both are correct. This is wrong, not correct. This is not correct. We cannot use more than one slash. So either we have to write it in this way. Joules, then one slash, then you open up a bracket and keep K and mole in between or inside the bracket. Then this is correct. Then K should be capital K here. Then this way we know that both K and mole are in denominator, it's divided. It divides J. This is correct. This is correct. Or else we can write joule, then both Kelvin and mole I'll take to top the numerator and by changing its index to -1. Then this is also correct, but always you are keeping a space in between. and this is correct. This is also correct. This is also correct. So we should not use more than one slash. Alright. Next one. What when we are representing plurals of units. For example, 100 kilograms. So what is the rule? Plurals of units. Plurals of units. There are two rules. For symbols, S or ES not used. That means 100 you cannot write kgs. You only can write is 100 kilograms. So 100 kgs not correct. And 100 kg is correct. But when you are using unit names, plurals can be used. It's like this: 100 kilograms you can use. So 100 newtons you can use. So 100 meters you can use. So here plurals with unit names. This is correct. This is also correct. This is also correct. Right? Keep in mind, when you are using unit symbols, you cannot use plurals. But when you are using unit names, yes, you are having the rights to use plurals, that is S or ES or whatever the grammatically correct way to represent or convert that to plural. Right. Next rule. This is a specific rule when writing thermodynamic temperature, no degree symbol used. Writing thermodynamic temperature, no degree symbol used. So, for example, 323 Kelvin, we are not using any degree symbol, but if you write 323 degree Kelvin, this is not wrong, not correct. This is not correct. And this is correct. Same, it relate to this, that's why I am writing it under this. When writing temperature in Celsius or Fahrenheit, then there are two specific ways. No space in between value and the unit. No space between value and the unit. That is, that for example 32 degree Celsius you can write like this, or maybe 98 degree Fahrenheit you can write like this. Both are correct. So here when you are using temperature in Fahrenheit, unit used, and the second thing is, and degree symbol is used. So for both the cases I explained that example, then these both are correct. This is correct and this is correct. Both the cases you have to follow this method, that is degree symbol. We have to represent degree as well as Fahrenheit and Celsius, the degree and space. Right. The last one, when you are representing figures, the values, always you have to keep them in scientific form. Unit values always keep in scientific form. Unit or the physical quantity values should be kept in scientific notation. Or scientific form, whatever contains you. For example, this is density of mercury. Normally we are not keeping this in this form. What we are doing is we are writing 1.3 into 36. 1.36 into 10 to the power, that decimal place I shift 4 places to left, 1, 2, 3, 4, so 10 to the power 4 kilograms per meter cube. This is correct. This is the correct way of representing. Correct way of representing. Presentation. Correct way of presentation. Yes. So when we are writing scientific, especially when we are dealing with scientific things or mathematical things, or especially the scientific things, we have to follow this rule. So the our value should kept in scientific form notation. That is always 1 decimal place and into 10's power. Alright. So these are the rules we should follow when we are doing scientific representation of our data. And okay, with this, the unit section is finishing, and that is the fundamental 46 subject, and whatever the theories we learn in this section apply all over the physics course. So you have to remember that, and you have to follow the rules what we discussed so far. Hope that is clear. So I'll erase it and we'll move to next section, that is dimensional analysis. So, dimensional analysis. Right. If I read out, then you can let me know. If not, then I'll move to the dimensional analysis lesson. Dimensional analysis. Right. We know there are basic dimensions or basic physical quantities of objects, and we define seven fundamental quantities or unit. Fundamental quantities of physical or units. We define 7 fundamental quantities or fundamental units, and when we are discussing or thinking about those fundamental quantities, those fundamental quantities or fundamental units are not only the quantities what we are dealing with. We will get some derived units or quantities as well. We will get some derived units and derived quantities as well. So mainly when we want to analyze the relationship between derived units and fundamental units, how that derived unit, maybe because for example there are specific derived unit is specific names like Newton, like Pascal, like Watt, like Joule, like Hertz. Those are derived units but specific names. So we know, even if someone knows physics and if you tell Newton, he'll understand what is Newton and what is Joule and what is Pascal. But these are derived units, these units are not directly represented with the fundamental units what we discuss here. But in some cases we need to understand what is the relationship between these fundamental units, so that this sort of exercises, activities are known as dimensional analysis, and for that one we define some symbolic representation of fundamental units or quantities. So that symbolic representation of fundamental quantities or units are known as dimension of the particular unit. So that you can write like this: symbolic representation of fundamental unit or fundamental quantity is known as dimensional representation or dimension of that quantity or unit. Right. So then we'll see what are those dimensions and how they relate to each other. So let's say we are having 7 fundamental units. So then physical quantities, let's say physical quantity. Physical quantity. Then maybe we can discuss about its units. Unit name, maybe symbol also, within bracket we will write symbol. Right. Then dimension. Yes. Next, dimension. So we'll see what are the dimensions for those physical quantities we know so far, the fundamental quantities, and later on we'll discuss about derived as well. Yeah, we know length, and length unit is meter, and its symbol is m, and for meter the defined dimension letter or dimension symbol is capital L. Dimension symbol is capital L. Then next, the mass. Mass, we know it's kilogram. It's kilogram, and unit symbol is kg, simple kg, and its dimension is capital M. Its dimension is capital M. Next, time. Fundamental unit for time is second, and its symbol is S, and dimension for time is capital T. Dimension for time is capital T. Right. are the basic dimensions we supposed to learn under advanced level physics. And in our dimensional analysis and further studies, we are not using other fundamental quantities we discussed already. But for your understanding and further knowledge, I'll give you the data for the other quantities as well, but they are not in much use under advanced level physics syllabus. So this is current or electric current. The correct term is electric current. Why? Because if you study further on this subject, you will understand there are many more currents you are discussing with. The unit is ampere, unit name, but here ampere is scientist's name. Because of that, the symbol is capital A, and dimension for current is capital I. Dimension for current is capital I. Then thermodynamic temperature. Thermodynamic temperature is measured with Kelvin. The unit name all simple Kelvin, but unit symbol is capital K because it's a scientist name, and the dimension for Kelvin is theta. It's a Greek letter theta. And next fundamental quantity we know is the substance amount. And its unit name is mole, M-O-L-E, and symbol is M-O-L. And the common dimension for the mole or the substance amount is N. When we are doing the dimensional analysis, we are using capital M to represent substance amount. Then luminosity. Luminosity, that is the amount of the dispersion we can see the light, or amount of the reflection or the illumination we can see, that is the measure of luminosity, or that is the meaning of luminosity. And the unit name is candela. And symbol is CD, simple CD, and for luminosity the dimension is capital J. Alright, so these are the dimensions for fundamental quantities we learned so far, and mainly the first three, that is length, mass and type, are much important and much used than the others in under this syllabus. Okay, hope you copy this, then I'll erase. Okay, anyway, yeah, Then I'll discuss some specific things about the dimensions. It's like this. There are, you can write a small note on this. There are units, sorry, there are quantities, there are physical quantities we come across which not contain both units as well as dimensions. Those are refractive index, because that is a ratio. Refractive index is a ratio, and coefficient of friction, that also sort of a ratio. Then relative density, relative density is some substance densities compared with water density, so it's a comparison. And then the relative humidity also a comparison. Okay, what is the possible humidity level of the particular environment within the particular temperature to what is the humidity having now, the comparison. The humidity is the known as this water, amount of water vapor what we are having in that particular this environment, or the environment what we are measuring, that is known as humidity. Amount of water vapor contains water in that particular environment. So it compare with the total possible amount of water vapor can have in that particular temperature in a particular environment. So that is known as saturated conditions. Maybe the terms will come when you are discussing about matter and materials. Right. Those quantities are not having any unit or physical dimension. Next thing is there. Okay, you can write a note. There are physical quantities which having unit but no dimension. They are having units but no dimensions. Those are plane angle and solid angle. Plane angle and solid angle, we know that they are having the plane angle, the unit is radian, and solid angle, the unit is steradian. Even though they are having units, but they are not defined with dimensions. Okay, right. So that is the introduction of dimensions, and we'll move to the section called dimensional analysis. Dimensional analysis. So there are few applications of dimensional analysis, but I'll discuss mainly two applications under this syllabus. There are more. So one application is applications of dimensional analysis. The first thing is it's like this. Okay, the check, first to check the correctness of the given relationship among physical quantities. among physical quantities. It's like this. For example, we are given an equation or relationship with physical quantities. That all our physics studies are with relationships and equations and or derivation of equations or relationships. So that if any relationship is given, before going into further studies of that or further experimenting that or further studying of that, we can check the correctness. So one way of checking that correctness is dimensional analysis. The next thing is derive a relationship among physical quantities. Physical quantities. It's like this. That we know some of the physical quantities are related to another happening or another incident or another physical quantities. For example, that when Newton doing his experiments or his understanding about the gravitational force, first of all he planned or he tried to understand what are the other parameters or what are the parameters or what are the physical quantities relating to this apple fall or falling of this apple. By assuming so many physical quantities, he extracted, okay, this might be the range of physical quantities related to this incident, and then he analyzed those things dimensionally and derived a relationship. For example, another great postulate or great discovery of Newton is the gravitational law or gravitational relationship, where he defined gravitational force is like this. So he initially assumed, okay, gravitational force is related to the weight, mass, then distance, maybe temperature, maybe maybe luminosity, I don't know, maybe time, like that. Initially he collected few parameters. Maybe later on he ended up with, okay, the gravitation is relating to these three, not the rest, right? Then he wanted to define a relationship, and using this dimensional analysis concept, he did that and he proved that, okay, this is correct. This, so dimensional analysis is used to derive a relationship among physical quantities. Those are the main applications we are supposed to learn under advanced level syllabus. And next thing is that if you are studying further on physics and the dimensional analysis, even you can convert unit of one system to another system using dimensional analysis, and then you can represent the nature of the physical quantities within dimensional analysis, but that is not, those are not under our syllabus, so we are not further digging into those things, and we will going in to before going into the further studies of these two concepts, and we'll discuss briefly on limitations of dimensional analysis. The dimensional analysis will not give you solutions at all conditions. It too limits to some extent. Limitations of dimensional analysis. Limitations of dimensional analysis. Yeah. First thing is it is not giving you the full idea about the dimension, not fully defining the dimensional constant. I'll explain you what is the meaning of this statement. It's like this. You know, we can derive or we can collect some information about physical quantities, and we can assume or we can postulate or we can build some relationship and say, okay, the particular quantities are relate to that maybe directly or inversely. Let's say this sort of relationship we can generate initially, and then I can write, okay, F m over R. Then next, to remove this proportionality, I'll introduce a constant what is known as proportional constant. Right? Proportional constant. Okay. This is known as dimensional constant, and with dimensional analysis we not always able to get the exact or correct idea about this dimensional constant and its dimensions and its magnitude either. We are not able to fully understand about this dimensional constant with dimensional analysis. That is one limitation of dimensional analysis. So dimensional analysis does not provide information about the dimensional constant. Right. Yeah. Next thing is the dimensional analysis not give you idea about the physical quantity, whether it's a vector or scalar. But here I cannot explain it with pictures or any explanation. It's like this. With dimensional analysis we cannot say whether that particular quantity is vector or a, cannot identify either vector or scalar nature of the physical quantity. The physical quantity. In dimensional analysis, we cannot understand whether that particular quantity is a vector or a scalar. That also another limitation of dimensional analysis. Next thing is, yeah, it's like this. Even though that dimensional analysis giving us the results that the relationship is dimensionally correct, but we don't know whether that is scientifically correct. So you can write like this. Third one, even though given relationship is dimensionally correct, it does not mean that it is scientifically correct. It does not mean that it's scientifically correct. Right. Again, if the relationship is trigonometric, it's like this fourth one, trigonometric. Like cos something or sine something, like that, or exponential, like e to something, e to x, like this, e to the unit length or width, like that. If this relationship or logarithmic like log into something or log natural into something, right? If these sort of relationships, if any dimensional quantities came across, dimensional analysis cannot use to analyze these things. So you can make a note. If the dimensional relationship is with trigonometric, exponential or logarithmic, then dimensional analysis is not used or cannot give proper results. Yeah. Those are few limitations of dimensional analysis. Even you will get more upon this if you read further or if you do further studies on this, but I limit that limitations to these few explanations. So what I wanted to give you the idea is, even dimensional analysis is not fully defined and it's not fully solving our problems. They too having some limitations. Okay. Now we will go to the example of dimensional analysis. So we said the dimensional analysis we are using for two specific purposes. That is to check the correctness of the given equation, and the other one is the final relationship between given quantities, right? And yeah, before that we learn about the small thing that is called the principle of homogeneity. Principle of homogeneity. Yes, because this is the main concept we are using when we are checking the correctness of for checking the correctness of given relationship. For checking the correctness of given relationship. given relationship. What principle of homogeneity says is, if let's say A equals B over C plus D over E, dimensionally correct, then dimensions of A should equals to dimensions of B within C should equals to dimensions of D within E. So this is what known as principle of homogeneity. And here I'll introduce another concept here, that is, instead of writing dimensions of A in P6, I can write this as A within square bracket, means now I am considering dimensions of A. This square bracket means the physical quantities dimensions I am dealing with. I am discussing, or I am extracting, or I am analyzing, or I am studying the dimensions of this A. That is the meaning of this square bracket symbol. Instead of writing these dimensions of A, simply I can write A. Then this one I can write B over C dimension. Dimensionally B over C. And next line, next I can write C D over E dimensionally. So in next stages, when we are doing dimensional analysis, we are not writing anything like these dimensions. We just use this symbol to say we are doing the dimensional analysis and we are considering the dimensions of this. Because remember that the limitations of dimensional analysis, we said, even though the equation is correct dimensionally, it does not mean that it's scientifically correct. So that is why we always equate in the dimensions and we are saying it's dimensionally correct. We don't know whether it's scientifically correct. Okay, this is what known as principle of homogeneity. Okay, make a note on that. So I will list this and we will go to some examples and see how we can use dimensional analysis to see the correctness of given relationship. Dimensional analysis to check the correctness of given relationship. is given a relationship of physical quantities quantities U, V and T, so U, V, A and T, U, V, A, simple A and simple T and T are relates to each other, relate to each other as V equals U plus A T. V equals U plus A T, where V and U are velocities. A acceleration, T time, T is time. So U and V are velocities. A is acceleration and T is time. Okay. Right. How we are doing dimensional analysis to check the correctness of this relationship. Okay. What we are doing is, first we check the dimensions of this equation in parts. In parts in the sense, now if this relationship is dimensionally correct, its left hand side dimension should be equals to right hand side dimensions. Right. So what we are doing is, we'll see. Now we are doing dimensions of left hand side. Left hand side dimensions. So left hand side dimensions, let's say it equals to dimension of V. V is velocity. Okay. You know, so I'll write the definition of velocity this time because it's a new term to us. Velocity equals to displacement over time. So then the dimension of velocity equals to dimension of displacement over dimension of time. Dimension of displacement is length, it is L, and dimension of time is T, so T. Either I can write like this, O L T minus 1. Right. Then dimension of left hand side, it is LT minus 1. LT minus 1. Okay. This is my first equation. First equation. So LT minus 1. Right. Then dimension of right hand side. Dimension of right hand side, it equals to dimensions of should, right, and it should equals to dimension of AT as per the principle of homogeneity. Yeah, as per principle of homogeneity, yeah, it should be like this. We know the dimension of u also velocity. So velocity dimension is LT minus 1, right? Okay. Then I can say this is 2. Right. Then dimension of AT. Right. So we'll see what is AT. Yeah. A is what? Acceleration. A is what? Acceleration. What is acceleration? Rate of change of speed. Or that is, or rate of change of velocity. Velocity over time. Then acceleration dimension equals to velocity dimension over dimension of time. Or else I can write the acceleration, if my symbol is A, dimension of A equals to velocity. Velocity is what? LT minus 1 over time is T. If I further simplify this with that Ulysses knowledge, then I can take T2 up and then it ended up with LT minus 2. Right. Then simply here I can write this equals to A's dimension into P's dimension. But A's dimension is LT minus 2. LT minus 2. But T is time, his dimension is T. This is multiplication. This is multiplication. Then T minus 2 multiplied by T positive plus 1, it ends up with LT minus 1. Right? That is my equation 3. So with, I can say 2 equals to 3. Now 2 equals to 3. Right. So now, okay, I'll give you 2 minutes. Copy this. First I want to erase this set apart. Right. We'll erase these, the definitions. Right. Then 2 equals 3. Then I can say dimension of right hand side equals to this, right? LT minus 1. LT minus 1. I'll say this is my fourth equation. Now, but now can see 1 equals to 4. So, dimensionally left hand side dimensionally equals to right hand side. Then I can say then with principle of homogeneity given relationship is dimensionally correct. So this dimensionally term is important. This dimensional term is important because that we know that the equation can be dimensionally correct, but scientifically it might not. That is why we are conditioning our solution by saying, yeah, it is dimensionally correct. Okay, this is one now. Methods we are using to do dimensional analysis and to check whether the given relationship is dimensionally correct. So with this I am planning to finish the class for today, and we are going to discuss some more examples on this same dimensional analysis and checking the correctness of given relationship as well as deriving some relationships and finding some unknown values in dimensional and given relationships next time. And hope you understood this concept to some extent, and if you don't understood or if you want any clarification, let me know. If not, I will conclude for today and we will meet next time. I'll give you 2 minutes to give your feedback if you need any further explanation on this.